Hello, welcome to Lab 8 for hydraulics.
What we're going to do is we're going to unpack Lab 9 and talk about the actual type of valve we're going to use in Lab 9. So it's all about a special kind of valve that meters and also kind of compensates by pressure. Yeah, it's a compensated flow valve, a pressure compensated flow valve. And it also does some metering, and there are actually a couple different configurations that we can use for this. I've actually got some diagrams that we're going to go just through the lab quickly, and I've got some like the actual lab instructions, and I've got some diagrams that I want to play around with, and of course I've got some cool stuff that we can play with. So before we go anywhere, I want to talk about principle. I want to talk about kind of metering. And what we're going to do is you have a pneumatic cylinder here. We're going to pretend it's hydraulic. Again, the principles of hydraulic and pneumatic controls are almost exactly the same. But you do know that air pressure does kind of different things mechanically than a pressurized fluid. So what I'm going to do is I'm going to kind of we're going to see. Actually, we're going to study how air pressure acts a little differently than hydraulic pressure, but we're going to see the principles of control are the same. Pretty cool. Okay, so let's go on here. What I'm going to talk about is a pressure compensated flow valve. Actually, let me jump into the lab first. Actually, I will go through the lab. Okay, so what's going on is that we're going to study metering out with a motor. So here's this motor, and we're going to study metering out with a motor, and we're going to be able to control the speed of the motor by throttling the fluid coming out. And then we're going to put a pressure compensated throttle valve in here, and we're going to see how that kind of changes the flow rate depending on the pressure. So that's kind of our shtick, and that's what we're going to do. So what we're studying is we're studying a motor, and we're studying the speed of a motor and the flow rate through the motor, depending on how we throttle it. And then we're going to change the pressure. Yeah. So what I'm going to do is I have this set up over here. Make sure my pressure's up. Okay, good. So I have a pneumatic setup over here. Let me put this out of the way. I got this pneumatic setup over here, and I've got the pressure up to 100 psi. That's fine. We're not going to use 100 psi in here. What I've got is I've got a cylinder, and I've got my pressure regulator. I've got it set to 0. And I am going to let air go into here, and this thing's going to move. Okay, that's fine. So we know that I can throttle how this thing moves. Let me sit here. We know that I can throttle the air coming out of this cylinder. And, whether this thing is hydraulic or pneumatic, the principles of control are going to be the same. What we're going to see here is that as far as the pneumatics go, we're going to see something interesting happen. We're going to see the speed of this thing change as it extends. And the reason is because the air in here gets compressed. Now, with hydraulic fluid, if we had a pump that was spinning at a particular rate, this thing, if we hooked it up to here, this thing would move at a very steady rate the whole time because hydraulic fluid isn't compressible. But because air is compressible, we're going to see this kind of start to go quickly and then go slowly and slowly and slowly and slowly because the air coming out here, I'm going to throttle the air coming out here. I've got a throttle valve on here. And what's going to happen is as this is going forward, dude, there's a lot of air. From here to there, this cylinder is full of air. So all of that air is going to be forced out here, but there's a throttle valve here. So back pressure is going to be created here. But in pneumatics, when we pressurize air, it compresses. But in hydraulics, it doesn't. So what's going to happen is that this is going to start to go out quickly, and then it's going to slow down and slow down and slow down more and more and more. And the reason is because as it expands, as this extends, the air coming out of here is actually compressing itself because of the motion itself. The air is getting compressed, and the pressure in here gets higher and higher and higher to the point where this thing moves really slowly. But what we're going to watch is we're going to watch the fact that this thing extends slowly because I'm throttling it. Okay, so as far as the hydraulic, I can put these up. As far as the hydraulic and pneumatic control goes, we're going to see the same thing. So if this was hydraulic, we would see this move at a very steady rate. It wouldn't go fast and then slow down and slow down and slow down. because there's no compression going on. But if I throttled this more, if I really cranked this down and throttled it, this thing would move really slowly. Okay, so that makes sense. If no matter what, if I'm doing that with hydraulics or pneumatics, we can see the fact that as I throttle this, this thing moves slowly. Now, you understand throttling. You get that. I keep calling it throttling because in this case, because we're using a motor, actually, and we're only doing a one-directional motor, we're actually throttling. We're not doing metering. Let me say it this way. We're metering by throttling only. Now, a meter valve has a check valve in parallel with it to allow for the opposite direction, right? So let me just go over here. Let me go over here. Okay, here we go. So what's going on is that we know that the flow is throttled by this guy. Now, what's this guy all about? Well, it's because we want the cylinder to move this way without any restriction. So the air that's going to come, let me just draw the air in blue. So the air that comes this way, it's going to go here and it's going to go, dude, there's restriction here. Forget about it. I'm going this way. And it looks at this and it says, oh, dude, this is wide open. I'm going to go this way and this way and this way. And then I'm going to make this thing move this way. No problem. It's going to move really very quickly. So we know that, and we know that that's why we put this check valve in here, so that it can retract quickly, but the extension is going to be slow because it has to go through there. Because when it gets to here, it says, oh no, I can't go that way. And it goes back up and does this. Okay, we get that. So now I'm going to close this. I'm going to go back over to here, and I'm going to open up this guy, and I'm going to say, dude, this throttle valve right here, this guy right here, he doesn't have a check valve. Why is it not, let me just zoom out, excuse me, why is it not like this? Why doesn't it have that? Well, the reason is because, take a look, the motor is actually going in one direction only. So the fluid coming in, the fluid coming out of here is actually going through, wait a second, the fluid coming out of here is going through here, and it's not going back. It's not going back. There's no reason, because what's going on is that the DCV is not controlling it both ways. So what's happening here is that I don't need the check valve here, because the fluid only goes through here, and it starts to get throttled a little bit as it goes through here. And we can see that because it's getting throttled through here, the motor is going to spin slowly. Okay, we're fine with that, and that's perfectly fine. Now, what we're going to do is we're going to watch this, and in the lab you're actually going to be studying this. You're going to do this, and then you're going to see that it slows it down. But then what you're going to do is you're going to crank up the pressure. You're going to crank up the pressure, and you're going to see when you crank up the pressure, the problem is this thing starts to spin faster when you crank up the pressure. So that could be a problem. It could be an issue where I want this motor to spin the same speed, and I want to be able to throttle the fluid coming out of here so that this motor spins at the same speed no matter the pressure. So if I increase the pressure or decrease the pressure, no matter what, this thing's going to turn at the same speed, and I can control it. The problem here is if I put just a throttle valve in, what's going to happen is that if I crank the pressure up, this thing's going to move more quickly. And if I lower the pressure, it's going to move more slowly. So this kind of works, but it doesn't work as well if I have pressure changes. What you're going to do is you're going to study the pressure on either side of this. And you're going to see that with a pressure compensated, pardon me, this guy is a pressure compensated flow control valve. What's going to happen is you're going to see a greater pressure on this side and a lower pressure on this side. What it's doing is it's actually inside here. As it's flowing, it studies the pressure, and it says, okay, if the pressure goes up, like imagine you're this valve and you're smart, and you say, okay, buddy, just turn the knob on this valve, right, to set it to a particular pressure. Okay, so buddy just set it to a particular orifice throttling. So what's going on? This guy is throttled a specific amount. So it's been squeezed to an orifice size that is been set. Now, that means the flow rate is a certain amount. but I want to keep the flow rate the same, even if the pressure increases. So what's going on is this valve actually studies the pressure after, and then it actually says, okay, so before, I want the pressure after to be the same all the time. And what it's going to do is it's going to change the size of this orifice. It's going to change the nature of the throttling so that the flow rate is the same. It's pretty cool. And what's going to happen is that, so you're going to hook this up, and then you're going to hook this up. All you're going to do is flip it to a pressure compensated flow control valve, and that's it. Now, the reason this lab doesn't have this guy is because we're controlling a motor only one way. If you wanted to control the motor, both ways, what you would do is you would actually take this guy and you would just do this. You know me with paint. Everything in paint. I get teased about it, eh? But I love it. So what I'm going to do is I'm going to do this. I'm going to put that in there, kind of, essentially. So what's happening is that if I had a system that was going both ways, I would put this guy in here, or I would put this so that it was like this. Okay, just pretend that's connected, right? So I would put that there, so that my pressure compensated flow valve is still working, but now I'm kind of a full metering valve, where if the flow rate was coming, let me just do this. Actually, let me put this. You know what? This is what we can do is, let me go over here. If I had a motor going both ways, that's better. This is what I drew this for. So if I was controlling a motor both ways, I took all of the other components out, like, you know, the flow valve and all of this. And I'm just saying, this is what's going on here. If I wanted to do it both ways, and I stuck this in, right, we can see that that would work just fine. Okay, we can see that that would work just fine, in that what's happening here is that when the flow is actually going this way, when the flow is actually coming here and going here and making the motor spin this way, it's gonna get to here, and it's gonna see this, and it's gonna go, oh shit, I can't go that way, I have to go through here. So it's gonna go through here, and that's fine. It will throttle, and it will slow the motor down. But when you do the motor in the opposite direction, so when the flow goes this way, it's going to see this, it's going to see restriction, so it's going to go here, and it's going to see a free path, and it's going to go this way, and it's going to make the motor flow. I mean, it'll make the motor run quickly. But the problem is, no matter how you look at it, if I were to change the pressure, I wouldn't be able to manage that flow as well. So then what I would do was I would do this. I would use this guy. Let me just finish off this line here so that we've got this. We've got that like that. Okay, good. So now what I'm going to do is I'm going to take this guy. Let me just put this line in here too. So Daisy. Just so I'm clear about what I'm talking about. Okay, good. So now I'm going to take this guy. I'm going to put him in here. Paste. Here we go. So now I've got this pressure compensated flow control. So what's happening here is that the same thing is going to happen when the fluid is coming out here. When the fluid is going this way, it's going to go this way, and it's going to get throttled by this thing, because when it goes here, it says, oh no, I got a blockage and it can't go there. So it goes through here and it gets throttled through here. But if I were to increase the pressure, the flow would not change, because the compensation of this guy is smart, because there's a feedback in there, and that particular feedback is going to say, oh no, the pressure's gone up. Actually, what we need to do is change the orifice size, so that it's going to actually lower. It's going to make the orifice size a little bit smaller, because what's happening is that because of the pressure is higher, it's actually being able to make more flow go through a smaller orifice. We don't want more flow, because we want the motor during spin, when the fluid is going this way, we want that fluid to be the same rate. So now what I'm going to do here is I've got this throttle valve. And essentially, it's no different from hydraulics, although the action is a little bit different. What I'm going to do is, this is throttled, I'm going to kick this up to 10 psi, and then I'm going to extend the cylinder, and we'll watch it move. Okay, I don't have an intricate control in here, so I'm going to have to rip the hoses apart to retract it, but that doesn't matter. Okay, so I just want to make sure I know what I'm doing here. I put my glasses on. I'm going to put this guy to 10 psi. Okay, 10 psi. It's all charged up, so the compressor won't come on. Okay, I'm at 10 psi, no problem. Now, I'm going to extend this. Let's just watch it extend, okay? So it's going to extend, and I've got my meter valve here, and we're going to see how it extends. I'm throttling it. Okay, and now we can see the speed is pretty slow. The reason it's changing its speed like that, so the compressor came on, we just let it go. Actually, I can turn it off. It's at 100 psi. All I need is 10. The reason it was moving like that really slowly is because the air was getting compressed. So now what I'm going to do is I'm going to release the air out of the system by opening the pressure regulator all the way, and I'm just going to pop this, and now I'm going to pop this and bring this guy down. Okay, so that was the speed at which it was moving. And it had that particular signature of motion because of two things. One is because I was throttling the air. The other was because as it was extending, it was actually pressurizing the air, and the pressure in here was getting greater and greater and greater. There was back force pushing against the air that was compressing it, and that's because it's air. But if it was hydraulic, it would move at the same speed the whole time. But we noticed the speed change, the signature of how it moved. Now I'm going to crank the pressure up. So I'm going to do it one more time, and then I'm not going to talk. I'm going to do it one more time, and then I'm going to release it, and I'm going to crank the pressure up to like 20 psi, and we'll watch it again. Here we go. So let's watch it at 10 psi. Okay, pay attention. And then, yeah. I'm just going to just do it. So it's nice and quick, so we can see the two working. Here we go. Okay, that's the movement signature at 10 psi. Here's the movement signature at 20 psi. It's definitely moving faster. Not a lot faster, but a little bit. Now let's crank it up. I'll let the pressure out so I can actually undo this. Let's go to 40. Actually, we'll go right up to 50. Okay, we did 10, we did 20. Now let's do 60. And here we go. It's still moving pretty slow at the top, but it's definitely moving faster. So, should we go higher? Let's go higher. So we're starting to study why we need a pressure compensated flow control. Okay, dude, I've got it at 100 psi. Here we go. That's moving pretty quick. So we can see that, let me turn this down. So what we have studied with fluid power control, whether it's hydraulic or pneumatic, we found that the actual throttling of the air or fluid out of an actuator, whether it's a motor or whether it's linear, is going to slow the speed of it or the rotation down. We know that. We get that. But what we've seen is if you change the pressure, it doesn't control at the same speed. So if I want to control my motor at the same speed with some kind of with a throttle valve, I have to make sure it's a pressure compensated throttle valve. So that's what's going on, and the reason it's pressure compensated, or I mean the symbol that we can see when we take a look at it being pressure compensated. So what's going on is that we can see that there's some pressure compensation here. It studies the pressure out here. Depending on what that pressure is, it actually adjusts this. It actually adjusts the orifice. As the pressure goes up, it actually makes the orifice a little bit smaller because it has to keep the flow rate the same. So we need some kind of feedback so we can see Lab 8.
All right, moving on to Lab 8. Now, Lab 8 is pretty cool. What we're going to do is we're actually using a motor, hydraulic motor, so spinning. And we're going to use a throttle valve to control the speed of them. We're going to look at pressures on either side of the throttle valve. And then we're going to actually use a pressure compensated throttle valve and kind of see how that affects things. And we're also going to change the pressure so we can see if changing the pressure either higher or lower is going to change the RPM of the motor. And we will see that it does, but when we use the pressure compensated, it won't. Okay, this is an easy.
Cool. So it was a nice easy hookup. So if we take a look at what's going on here, you can see there's my DCV. My motor's actually over here. You can't really see the motor, but anyway, believe me, it's there. Now we can see everything. So there's the motor, there's my DCV, and I'm looking at a flow valve. So I'm just studying the flow of the liquid coming out. Actually, let's go back to take a look at the diagram. Hold on a second, guys. Let's just go over here because that's what the pressure compensation is. What we're doing is we're studying the flow just before the tank. We're studying the flow after here. But as you know, just like in an AC circuit, the current right here is the same as the current here, is the same as the current here, is the same as the current here, and the same. So I could put this flow valve anywhere in here and it would read the same thing. So we're looking at the flow rate here, and we've got, now that's just the system pressure, as you guys know. Now, these are the two pressures on either side of this. Now, in this case, I've got it hooked up just the throttle valve. Over here, this guy down here is the pressure compensated throttle valve. And you'll see that when it's running, let's study the pressures on either side when it's running.
Pressure on either side. There's a little bit of pressure on this side and zero pressure on that side. As I'm turning this, watch my flow. So I'm going to turn this until I'm going to turn it clockwise. I'm throttling until I've got 1 gallon per minute. Okay, so I'm at 1 gallon per minute. Look at the pressure differential.
So what's going on is that I've got pressure on this side, no pressure on this, because this is just seeing tank. It's just seeing the tank. So what's happening is that because this is throttling, it's creating back pressure, which actually kind of is slowing the flow down, and it's saying, no, dude, no. It's just like adding a resistor to the circuit. So it's slowing the flow down, and we're seeing pressure on this side. So you know what? This is just like a resistor. It's like a resistor in a circuit. The reason that we see a voltage drop across the resistor is because there's energy being used up. And the same thing here. The reason we see pressure across here is because this thing is actually using up energy. It's actually doing some work. It's slowing the flow down. Now, what I want to show you is what happens when I flip it. Now, you can see, wait a second. Let me go. Okay, there you go. So now, did you see? That was cool how it jumped down here. So what's going on is that now I'm using the pressure compensated flow control valve. And in this case, when we run it, we're going to see a pressure over here.
Rate change will actually change the speed of the motor as well. Okay, so maybe in lab we can hook it up to another system.
Okay, here we go.
And I'm going to increase the pressure and we'll see if the flow rate changes. Okay, I'm going to increase it, and as I go up to 500, let's just see if this changes. Cool. Pressure compensated throttle valve. So cool.
So like I said, the pressure goes up here. I think I said that we're going to see pressure here, but I meant to say that we're going to see a high pressure over here. So the pressure drop across this is greater, just like the voltage drop across this would be greater. So essentially what's going on, dude, it's kind of like putting a variable, it's kind of like a pot that there's a controller that runs over to the pot and changes the resistance of the pot depending on the voltage. So if the voltage changes and you still want your, if I were to say, let me go over and draw a circuit. Let's say I always want the voltage drop across this to be 10 volts, no matter what it is. Let's say it's a motor or a lamp or a light, doesn't matter. And I were to change this to 40 volts. The problem is the voltage drop across this would get greater, and you know that. But if we wanted to keep it at 10, I would make the resistance of this increase. So it would take more of the voltage drop of this 40, and it would manage this to be 10. So if this kept moving, if this was variable, and I increased or decreased this depending on other loads on the circuit, and I think you guys may know this, but if I were to do this, And so I'm talking about more of a hydraulic system here, but let's just say I took a connection over here and I put this onto a motor, right? And this is a really, really heavy motor. Its resistance is like, I don't know, 0.1 ohm, okay? So now I'm going to put a switch in here. Let me just put a switch in here. Okay, this is a switch in here. That's fine. So now I've got this switch in here. That's fine. So now what's going on is that this is all running. It's all good. It's all fine. And this guy has a voltage of 40 volts. That's no problem. Or, I mean, let's go back to the fact that this was 30, this was 10, and that was 20. Now what happens is if I were to close this switch, this draws so much current that the battery, it can't handle that. It can't handle that much current. It says, no, dude, I can't give you that much current. And what happens actually is that the voltage, the power of this, the pressure coming out of here lowers. And there's actually going to be less than 30 volts. This may go down to 27 volts because this is stealing so much of the energy from here that these guys aren't going to get as much energy. But I do not want this to dim. It's a lamp and I do not want it to dim. So what I'm going to do is I'm going to put a pressure or a voltage compensated resistor in here. And then what it's going to do is it's going to constantly study the pressure on either side. And if the pressure goes low here for whatever reason, it's actually going to make this a larger resistor or a greater resistor, more or less, to make sure that the flow rate through here is going to be consistent all the time. And you know, if the flow rate is consistent all the time, no matter what this is, this could be 10 volts, it could be, sorry, this could be 30 volts, this could be 100 volts, this could be 62 volts, doesn't matter, whatever it is. If I want this to always have 10 volts, I have to ensure that the same flow rate goes through here all the time. That means that the voltage drop across it's going to be the same and the power in it's going to be the same. What happens in hydraulic systems is that you may ask the question, okay, well, I get that. I get the fact that we need this pressure compensated flow control valve because my pressure may change. And if it does change, I still need the same flow. So I'm going to make sure that I have this orifice, the size of the orifice is compensated for either a greater pressure or a lower pressure. But you may ask, well, why does the pressure change? Well, in hydraulic systems, what's going on is that the pump itself, it only has some power in it. And if I were to say, this motor has to run at the same speed all the time. And if I were to have some other process that was coming on and off, what's going to happen is that the pressure coming out of that pump or the pressure in the entire system may fluctuate a little bit, may change, may go up and may go down. And that's going to change the speed of the motor. You don't want that. So it manages fluctuation. Also, we could have a system where we need to change pressure for lots of different reasons. Maybe there's an actuator that needs different pressures, or maybe the whole system needs to have different pressures up or down depending on some of the other components. But you want the motor to flow the same the whole time. So you put a pressure compensated flow control valve. I think I've covered everything. Any questions? Because really just did cover everything. So if there are no questions, I'm going to end the recording so that people watching this can just go. So I think I'm good. Goodbye.